We're going to do some examples using the limit comparison test. Let's first start with an example that we did the regular comparison test for. The sum k goes from 1 to infinity of 1 over k squared minus 5k plus 1. If you remember when we did the regular comparison test, first we said that 1 over k squared minus 5k plus 1 was positive for k bigger than or equal to 5. We went on to show that we could compare it to 2 over k squared for k bigger than or equal to 10. And it was kind of complicated to figure out that that's what we should compare it to and for what values of k would work. So let's see if the limit comparison test will be any quicker. We know that 1 over k squared minus 5k plus 1 should act like 1 over k squared for large k. Again, we're looking at a rational expression and looking at just the leading terms. And so let's try comparing it to 1 over k squared. We do still have to say that we're only doing this test for k greater than or equal to 5 because the limit comparison test also requires that all the terms be positive. So let's look at the limit as k goes to infinity of 1 over k squared minus 5k plus 1 divided by 1 over k squared, which is the limit as k goes to infinity of k squared over k squared minus 5k plus 1, which is just 1. So either both series converge or they both diverge. But we know that the sum k goes from 1 to infinity of 1 over k squared converges. It's a p series with p equal to. So the series we care about from k going from 5 to infinity, because we can only use this test for k bigger than or equal to 5, also converges by the limit comparison test. And then, of course, if we know that the sum converges eventually, we get that k goes from 1 to infinity of 1 over k squared minus 5k plus 1 converges, because adding on those extra 4 terms is not going to change whether it converges or not. Just the answer it converges to. So as you can see, that example was much, much easier with the limit comparison test. We didn't even have to try to guess whether it was going to converge or diverge before taking the limit. Let's look at another example. Let's look at the sum k goes from 1 to infinity of the square root of k cubed plus 1 divided by 2k to the 4th minus 1. So this one looks complicated, but all we really want to know is kind of what power of k does this act like when k is large. So let's look at the leading terms. So we're looking at the square root of k cubed plus 1 over 2k to the 4th minus 1 is approximately the square root of k cubed over 2k to the 4th when k is large. And now we can reduce that a little bit. We can get k to the 3 halves over square root of 2 k squared. And simplifying that even more, that would be 1 over the square root of 2 k to the 1 half. But we don't even have to worry about that square root of 2, because the nice thing about the limit comparison test is we don't have to find something that it, is exactly the limit is going to be 1. We need to find something where in the limit we're going to get a constant. So, any constant times the thing we want to compare to, we don't have to worry about that constant. So what we're going to do is compare with the sum k goes from 1 to infinity of 1 over k to the half. And note, that one's always positive. And we also want to worry about our original series always being positive. The only thing that might be a concern is the bottom, but even if we take 1 and we raise it to the 4th, multiply it by 2, that number is going to be bigger than 1. And as we make k bigger, it'll still be bigger than 1. So this series is always positive. But you do want to make sure that you always check. All right, so we're going to compare with this series. And we know that this series diverges because it's a p series, p equaling a half. So let's look at this limit and see if we can actually make this comparison. So limit as k goes to infinity of k cubed plus 1 over 2k to the fourth minus 1 to the half. And I'm going to go ahead and flip the 1 over k to the half already. So this is k to the half over 1. Dividing by 1 over k to the half is the same as multiplying by k to the half over 1. And since everything here is actually to the half, I can go ahead and combine it. So I get the limit as k goes to infinity of k cubed plus 1 times k over 2k to the fourth minus 1, all to the half, which gives me the limit as k goes to infinity of k to the fourth plus k over 2k to the fourth minus 1, all to the half. Now, dividing through by k to the fourth inside the half, I'm going to have limit as k goes to infinity of 1 over k to the fourth divided by 1 over k to the fourth times k to the fourth plus k over 2k to the fourth minus 1 to the half. So notice I'm just multiplying by 1, so it doesn't matter that I did it inside the half. And then this is the limit as k goes to infinity of 1 plus 1 over k cubed divided by 2 minus 1 over k to the fourth, all to the half. And now we can see that that limit is going to be 1/2 raised to the 1/2, which is the same as 1 over square root of 2. And this is a constant. It's bigger than 0, it's less than infinity, so we can use the limit comparison test. And so by the limit comparison test, our series that we care about diverges, since we already showed that 1 over k to the half diverged. Let's look at the next example. So this is the series k goes from 2 to infinity of 1 over 5 to the k minus 2 to the k. So again, we want to check that this is positive, but 5 to the k is going to be bigger than 2 to the k for all positive k. So we have no problem there. And then what happens when k is large? What do we want to compare this to? Well, the 5 to the k is bigger than the 2 to the k. So let's make a guess that that 5 to the k is going to be the dominant term when k is large. So let's say 1 over 5 to the k minus 2 to the k is approximately 1 over 5 to the k when k is large. And the way we check that this guess, if this guess is true or not, is that's what we're doing when we take the limit of a to the k divided by b to the k. That's checking whether those actually grow at the same rate. So let's go ahead and take this limit as k goes to infinity of 1 over 5k minus 2 to the k times, and then I'm going to go ahead and flip it already, 5 to the k over 1. So again, multiplying by the reciprocal is the same as dividing. So now I have a 5 to the k on top, I have a 5 to the k and a 2 to the k on the bottom. Not really sure what's going to happen. So what I want to do is go ahead and divide through by 1 over 5 to the k in both the top and the bottom and see if that will help. So now I'm looking at the limit as k goes to infinity of 1 over 1 minus 2 to the k over 5 to the k, which is the limit as k goes to infinity, 1 over 1 minus 2/5 to the k. And 2/5 is a fraction less than 1, so that's going to go to 0, so this limit is 1. That means I'm allowed to use the limit comparison test to compare these two. But I know that the sum k goes from 1 to infinity of 1 over 5 to the k is a geometric series. I can rewrite this as 1/5 to the k. And so it's geometric with r equaling 1/5, so it converges. Therefore, the series we cared about, which was the sum k goes from 2 to infinity, remember it doesn't really matter where we start, of 1 over 5 to the k minus 2 to the k converges by the limit comparison test. Let's look at another example. This is the sum k goes from 1 to infinity of natural log of k squared over k squared. Now this one's a little bit harder than the others we've done. So before it was pretty obvious what we wanted to compare to, but if we're looking for something with the same rate of growth, that's kind of exactly what we already have. There's no extra constants or terms added on. So let's see what we can compare with. We know that natural log of k is kind of less than putting in a power of k. So what if we just tried to compare with 1 over k squared? Well, if we do that, let's look at this limit. Limit as k goes to infinity of natural log of k squared over k squared times k squared over 1, multiplying by the reciprocal. You can see those k squareds are going to cancel each other, and so we're looking at the limit as k goes to infinity of natural log of k squared, which is infinity. So it's not a constant between 0 and 1. And so, you might be thinking, oh, I can't apply the limit comparison test. But actually remember that you might still be able to apply it, because there was these extra conditions where if you got a limit of infinity or you got a limit of 0, it still told you something. So what does it tell us if we get this limit of infinity? Well, it tells us that if we know that the thing on the bottom, which maybe by writing it this way, I don't know what thing was on the bottom. So let's say that ak is natural log of k squared over k squared, and bk was 1 over k squared. We're going to look at the limit as k goes to infinity of a sub k over b sub k. So that's the natural log of k squared. Maybe I should write it this way. The limit as k goes to infinity of the natural log of k squared over 1 over k squared. Okay. So why am I writing it out as a fraction? Because we actually know if we take this limit and we get infinity, it does tell us something. It tells us if b sub k diverges, then if the sum b sub k diverges, then the sum a sub k diverges as well. And I guess this should make some sense, because it looks like, if we're getting infinity here, then the thing that was on the top of the fraction must have been bigger in terms of growth rates. So if the smaller one is going to go to infinity, then the bigger one should too. So now the question is, does the sum b sub k diverge? So we have the sum 1 over k squared. K goes from 1 to infinity, but that converges because it's a p-series with p equal 2. So what can we conclude from that? Absolutely nothing. We don't have any other criteria to use the limit comparison test. We got infinity, but we didn't have a bk that diverged, so the test is inconclusive. So we don't want to give up on the limit comparison test, though. Let's just see if we can compare with something else. So what if we try comparing with the sum of 1 over k? So why would I pick that? Well, 1 over k squared converges, and I wasn't able to use that to show that my series converged. Maybe my series actually diverges, and that's the problem. Well, 1 over k diverges, and it's something that in some sense just barely diverges. So let's try comparing with that. See if we can figure anything out there. So let's be formal about it again. So let's say that a sub k is natural log of k squared over k squared, and b sub k is 1 over k. And let's look at the limit as k goes to infinity of a sub k over b sub k, which is going to be the limit as k goes to infinity of natural log of k squared over k squared times k over 1. Well, now we can reduce one of those k's, so we're looking at the limit as k goes to infinity of natural log of k squared over k. And well, that's not as obvious what happens to that. What are we going to do? We're going to need to do L'Hopital because we've got an infinity over infinity type form. So let's say that this equals, by L'Hopital, the limit as k goes to infinity of, I need the chain rule on the top, so 2 natural log of k times 1 over k times the derivative of the bottom. At the bottom is just k, so its derivative is 1. So this is the limit as k goes to infinity of 2 natural log of k over k. And now we actually know by growth rates this is going to go to 0. But if you want to check that, we can try L'Hopital one more time. And so this is going to give us, maybe I should write my equals over here, the limit as k goes to infinity. If we do L'Hopital again, we get 2 over k over 1, which is 0. So what can we say if this limit equals 0? Well, again, let's go back and look at what your limit comparison test says. It says if the limit equals 0, then we can only say something if the sum of b converges. It says if the sum b sub k converges, then the sum a sub k converges. But we have a sum b sub k of 1 over k, which diverges because it's harmonic. So again, we are at an impasse. This is inconclusive, but it's inconclusive for the opposite reason. Instead of the limit being too big, it's too small. So now you might want to give up, but let's try one more thing. Let's try comparing with 1 over k to the 3 halves. So why would I pick that? Well, I tried 1 over k to the first power, and it was too small of a power. I tried 1 over k squared. That was too big of a power. So let me try something in the middle. Maybe that'll work. So what can I say? Well, first let's take this limit and see what happens. So limit as k goes to infinity of, again, our a sub k is natural log of k squared over k squared, and our b sub k now is 1 over k to the 3 halves. So we get natural log of k squared over k squared times k to the 3 halves over 1. And we can simplify this a little bit. We can get, this is the limit as k goes to infinity of natural log of k squared over k to the 1 half, k to the 3 halves over k squared. And this is going to infinity over infinity, so let's try L'Hopital. And we're going to get that the limit as k goes to infinity of 2 natural log of k times 1 over k from the chain rule divided by 1 half k to the negative 1 half. So what is that? That is the limit as k goes to infinity of, well, let's see here. We have a 2 natural log of k on top. We have a k on the bottom and a 2. Wait, that 2 has a half on the bottom, so that becomes a 2 on the top again. So there's another 2 on the top from this half. And actually, okay, wait. So we've done this 2. We've done this natural log of k. We've put this k on the bottom. This a half becomes a 2 on the top. And this k to the negative half should become a k to the half on top. Now we've got everything with positive exponents. So simplifying that, we get limit as k goes to infinity of 4 natural log of k over k to the half. Okay, well, I guess we've made some progress because now we only have natural log to the first power instead of natural log squared. So let's try L'Hopital again. Or if you were smart, you would know from growth rates, again, that any power of k is going to grow faster than a natural log of k, so this would be 0. But let's do L'Hopital and we can show it. So we get limit as k goes to infinity. The derivative of the top is 4 over k. The derivative of the bottom is 1 half k to the negative 1 half. And rewriting that, we get limit as k goes to infinity of 8 over, well, the k from the top is going in the bottom, and the k to the negative 1 half in the bottom is going to the top. And simplifying that, we get limit as k goes to infinity of 8 over k to the half, which goes to 0. Okay, now you're like, we've got 0 or infinity every time. How is this any different? Well, remember what we said about if you get 0. If you get 0, and the sum of the b sub k's converge, then the sum of the a sub k's converge. But this time, the difference between this time and when we did 1 over k is that the sum of 1 over k to the 3 halves, k goes from 1 to infinity, does converge because it's a p-series with p equaling 3 halves. So, by the limit comparison test and by those extra statements at the bottom of the limit comparison test, we know that the sum k goes from 1 to infinity over the natural log of k squared over k squared converges.